Fantastic, Leon. So as you guys know, computational design is such a broad topic, and most times it leaves students and even seasoned professionals confused. Or at best, it gets used early on in the design, either, programmatic explorations or form finding. And honestly, computational design is not a silver bullet, right? It's a methodology that's applicable at every phase of a project's life cycle and beneficial to any roles within the A&C industry. And in light of Cody's mission, we'll be exploring the application of computational design methodologies in technical design and digital fabrication with some amazing guests who I'm so excited to introduce, some of whom I've worked with. But for us to probably explore this topic, we have two parts to the event: a presentation and a panel discussion. So for the presentation, again, we ask that you post all questions using the Zoom Q&A feature, and feel free to vote certain questions up so that they get answered. So to kick things off with the presentation, allow me to introduce my buddy Gustav Fagerstöm, a registered architect and digital practice leader with Walter P. Moore Engineering, New York, where he leads the computational modeling for structural and facade engineering. Having global experience at all stages of the project lifecycle in over 10 different countries, he specializes in design computation at the intersection of architecture, engineering, and computer science. His work has been exhibited all over the world, in Europe, America, Asia. He's presented at Autodesk University, Acadia, Fabricate. He's a part of the Smart Geometry conference. He's also faculty at Pratt Institute and consultant on pen design. So for those who don't know, he's actually some musician. I don't know if he wanted me to say that, but yes, he is. So Gustav, take it away.
Thank you, Zubi. I play. There's a reason why I didn't make music my profession. So most people never get to hear it, but I enjoy it. Thank you so much for the invite. This is really great. I'm very happy to be here with this lineup and this great kind of set of lectures that you guys have been putting on in this wonderful setting of Code Detroit. This is really great. I will be speaking for, I think this will take about 45 minutes, but we'll see exactly how long that lasts. And I think also, Lauren, I'll pause maybe once or twice. If questions are coming in, we can take them as they come. I'm not great at multitasking though in that way, so I won't be able to read them. But if you think that there is anything, important to catch on the fly, then I'll pause and see if there's anything. Otherwise, we'll take it at the end, I suppose. Okay, so let's see if the mysterious screen share works and the mysterious presentation view. And not sharing that, maybe. How does that look? Yeah, good, okay. Okay, so I work for a company called Walter P. Moore. We are an engineering firm that has its origins in Houston, Texas, and who has been doing civil and structural engineering for a long time, actually since the 1930s. In the last 10 years, give or take, the division of facade engineering was born, and that's the one that I am specifically part of in the New York office. And in the last 5-6 years, we've done a lot of really interesting. Walter P. Moore itself is known for long span structures and retractable roofs, large scale projects in general. And when facade engineering kind of came about in a very sort of well-rounded and experienced engineering practice, it kind of took off with the hit the ground running, so to speak, and has done a lot of work in the relatively short time that our group has been in existence. And I'm very happy to be part of that almost from the beginning and from the very beginning in New York, and look forward to you know, where we take that next. And obviously we put a very heavy focus on computational design systems, and on following through with that. This is kind of the theme of today, like following through with that from very early stages, kind of option studies, where everything is pretty fluid, and all the way to the construction stage. And we actually have a quite frequent involvement also with fabrication modeling, where we take projects and we do the modeling for the fabricators and engineering for the contractors. So I'll be talking today about a project that was a little bit more of a traditional design bid build type delivery, but with still some early contractor involvement. I'll get to that a little bit later, why that is important to this presentation. Here you can see, just on a general note, here you can see kind of our company, where we do most of our work. It's a lot of it is in continental US, but we do work elsewhere in the world, and have offices also in a couple of other countries like Canada, Panama, and India more specifically. Some kind of projects of note before we go into the specific one I'm going to talk about here is, from top left, you got the Jacksonville Jaguars practice field in Jacksonville, Florida. Then over to the right from there is the Lucas Museum of Narrative Arts in Los Angeles, California. Here we have the Academy of Motion Pictures Arts and Sciences in California as well. Over to the right again is the Allianz Arena, which is the field for the Minnesota United. Here is the Gatehouse for the Golden State Warriors Arena that we'll be talking about today. This here is at the Angle Lake, SeaTac, and this is actually a rendering that is old, and I don't want to talk about it because the project is not built. It's the one I'm going to talk about today. Here's the Rams Stadium, again, recently inaugurated in LA. Here again, today's project. This is the new. This is a new terminal for the New Orleans Airport, the Armstrong Airport in New Orleans, Louisiana. And this finally is the so-called Mars Pavilion that was built out of robotically fabric-formed concrete for an event that Amazon held a couple of years ago. So there's a lot of different scales and kind of typologies of buildings that we get involved in, and today we'll specifically be talking about the kind of deep involvement we have in sports, and that all started actually with this here building that you might recognize. This is the Astrodome from 1965. This was done without any computational design tools, and still was done, of course, and is still going strong. And of course, being involved in kind of complex, long span architecture and structural engineering so early on, our team has had a very long tradition in kind of figuring out how to work together with architects, with other engineering consultancy disciplines, and how to sort of deliver difficult projects, even with fairly complex setups, and just in terms of like how the design team is structured, for instance. And I'll get to that in a second, on the note, in fact, of working together. So the case study of today is the Chase Center. Its official name. It's the Golden State Warriors home turf in the San Francisco Mission Bay. This is an area that used to be called the Dog Patch. And as some of you might know, the Warriors were a team in Oakland on the other side of the water from this photo, until they somewhat controversially, for many people, were moved into San Francisco proper. That is an issue that I take no position on, but that was something that many people cared about quite deeply, and hopefully the existence of a top class home field can offset some of the sense of that, you know, whether they should have moved or not, depending on where you stand in that question. And the reason, I think one of the reasons why this has become a really successful project is that it's part of a larger urban intervention here. So if you can see my mouse on the screen, it's sort of all of this here is about, if I'm not mistaken, about 500,000 square feet of mixed-use development with the arena at its center. If you have worked on sports projects yourselves, you might know, be familiar with that some of them tend to kind of land a little bit like an alien presence in the city and not really relate much to its surroundings. And I think that the team that did the master plan here, they did a really good job at avoiding that and to insert it in a urban context where it sort of makes sense and where it interacts with its surroundings, and it creates, you know, very successful, in my opinion, public space, which has been very well received and well visited. So this was completed in September, I think, of let me think now, September 2019, and I had the good fortune to visit once before traveling became difficult, as you're all familiar with. It's an 18,000 seat arena. And it also has a wealth of different kind of concerts and other public performances, which are supposedly great. I have not had the chance to actually see something in there, so that's on my to-do list still. So the very origins of this project were with a delivery method which is fairly common, especially here in the US, and I'm sure that many of you are familiar with it, which is the one in which there is a design architect, there is an executive architect, and then there is a set of consultants. In this case, the design architect is a firm called Manica, who are based in Kansas City, and they are very experienced and well-versed in sports projects. And then on the executive architect, the architect of record side, is a firm from Houston called Kendall Heaton Associates, who are also very experienced in delivering and executing projects and being the architect of record. However, when two firms with that sort of specialization need to take a project from the very early stages all the way to construction, especially in the kind of specialized building design systems, for instance, the facade system, there is a need for kind of a gap to be bridged, if you will, and that's where Walter P. Moore sat in this project. So our scope was between an architectural design intent and a set of bid construction drawings. Was our task then to formulate and devise enclosure systems, do the enclosure engineering, geometric rationalization, discretization, and detailing, delivering that in the form of 3D models, both for enclosure and the secondary structure that holds up the enclosure, as well as a set of typical details. And of course, reporting the loads imposed on the primary structure from our systems. So I'll get to all of that, and specifically this will be about the piece that has to do with geometric rationalization and discretization, and also a fair bit about how the kind of quirks of how this product was delivered because of a series of different factors, really. So when we talk about rationalization, I'm sure that if you are geometry nerds like me, then you will have heard this, you will have worked with this, you will have undertaken exercises in the interest of sort of rationalizing things, and yet maybe it's a little bit hard to actually exactly pinpoint what it means to rationalize something for construction in this case. So we did a kind of musing on this a few years ago in a white paper that we wrote, talking about what it might mean to rationalize something in architecture, engineering, and construction. So as you might remember from math class, this is the mathematical definition of a rational number, where Q is not equal to 0. Now, rationalization then in geometry is actually a little bit counterintuitive, right? Because, for instance, the geometry that we often deal with and that we often find ourselves having to quote unquote rationalize is, in fact, strictly speaking, rational. NURBS, as you will probably be familiar with, means non-uniform rational B-spline, and that's because the NURBS geometry is, from a mathematical and computational geometry point of view, rational. So surfaces and curves are mathematically rational. However, that doesn't necessarily lead to a construction rationale. And that is maybe what we're after when we're trying to, again, quote unquote, rationalize something in a construction sense. So with rationalization being in a way kind of jargon in AEC, without a really universally established meaning, we have attempted to define it for ourselves, meaning inside of our computational design kind of expertise within our firm, not necessarily claiming to have defined it for the Oxford Dictionary, but certainly for ourselves, it's useful to put some precise meanings to terms that we use. So in the case study of this project, the Golden State Warriors Arena, there is you might think of it as two different levels of rationalization, where if you look at the left side here of this slide, the level 1 so-called rationalization is a large scale one, which aims to describe overall building geometric entities with various basic geometric equations, those that can be kind of, that are the simple parametric ones with lines, circles, ellipses, planes, and spheres, etc. And then as you zoom in, as you go down in scale into kind of more actual architectural assemblies and components that are like physical pieces of stuff, then the level 2 so-called rationalization comes into place, where the overall global geometry, the one seen on the left here under level 1, will be divided into discrete, in this case, planar elements with one-dimensional edges. So that is, a roundabout way of saying discretizing or tessellating or panelizing, whatever it is, depending on what kind of project you're working on. So in this particular case, it was about making flat, four-sided sheets, which are eventually going to be made out of metal and become a metal panel rain screen. And so at the start of that exercise, we have this. This is the surface model. There is more resolution to this, but this is the sort of global geometry that is given to us and that represents the front of cladding from kind of the design intent. And this, I think I'll get to that a little bit later. This obviously has undergone much work before it even gets to this point. But the point of the discussion here is that this needs to become this, and most of the work to go between those two stages of existence were, I should say, because the building has been built within Wolfe Moore's facade team's scope of work. So if we zoom in a little bit and look at what's actually the kind of architectural system here at play, this is if you look at the exploded axonometric, you see to the back there are the primary structural columns who are engineered by somebody else. We did not do that. So our system comes into play at that interface, where these struts here that are, if you see the double triangle here, creates a moment connection, so that this top horizontal tube here, which was known as the hoop, becomes a moment stiff gravity connection. So that's where all the self weight of the whole system is taken up and goes back via these struts here into the primary system. Then the lower end of the panels are pinned. So these here, it's a little bit hard to see in this view, but you'll see that later on the mock-up picture. So these struts here are pinned so that they, whenever the wind blows, the lateral forces that affect the building, they get transferred back here, but any self-weight is taken up, including the weight of this. The lower hoop is taken up by these hangers and goes back through this hoop and back through these gravity connections here. So this is basically a rain screen, where back here you see those are the cold form studs that are at the level of the slab edges, which is then where the sheathing and the waterproofing and the insulation will be attached. So the kind of assembly logic of this is like a curtain wall. If you're familiar with how those work, they are usually top hung. So you have your gravity connection at the top, and then you have a lateral pin only at the bottom. And the exact same thing goes here, except that the weather barrier is further back, like in a rain screen. And so this is basically the, you see the section here to the left. There are these sort of different kind of steps in and out so that we can maintain flat mega panels always. I'll get back to that as well, which is quite important. And as the fabricators here in the room will know too, that makes their life a whole lot easier. The sort of primitive version here is basically you have the dashed line, which is your climate barrier, and the blue kind of kink line there is your visual skin that's seen from the outside in a complex shape. In the middle here, those are very simple, those are parallel, and then what we ended up doing so they can actually be split into manageable parts that can be assembled, transported, and installed. This is actually what comes out. And similarly, in terms of like conceptual geometric studies before anything actually sort of takes very final form, we did dozens and dozens of fairly quick hits in the earlier stages of different global area studies, like what would happen if you depending on the different offsets between structure and facade, how does that affect the square footage of the surface area of the facade, which is quite impactful to budget when you're dealing with these sort of surface areas involved in kind of big buildings like this. So you see this would then lead to kind of early stage costing, which can be roughly compared then to what the kind of the general contractor has put forward in their work towards a GMP. Now we don't get into costing proper, of course, because then that is usually a good deed that doesn't go unpunished, but it's nice sometimes to be able to keep track of this stuff just even for internal purposes and kind of sanity checks every now and then. I'm going to skip this in the interest of time. This is more, deep dive into what the engineering of the secondary system does, and I think we can skip past that. So these are some vignettes in sort of early submissions just to show assembly logic of the secondary structure in a drawing format. Now we get to the rationalization. So here you have the different actual pieces that were defined based on that Rhino skin geometry that we were given. And these are called things like drums and ribbons and ATW means atrium west, ATE means atrium east. So we came up with this fixed length delimited naming scheme, which again, for computational purposes, you all know that it's pretty nifty to be able to always know what's on a certain position in a string, for instance, when you're querying something. So that was the sort of philosophy behind here, that you have a 3 plus 1 or 3 plus 2 or 3 plus 3 sometimes nomenclature, where the hyphen is the one that divides the kind of category from the specific position. Makes it a lot easier when you crunch the data later on. This is the level 1 rationalization, where we're deciding what is a discrete abstract piece of global setting out geometry, you might say. And how is that then defined? And the reason we're embarking on this exercise at this point in time, this is about halfway through DD, if I'm not mistaken, is that because of contractual reasons, there's a sort of back and forth where sometimes this project is supposed to be delivered in 3D. So we have actual 3D model based procurement. And then that goes away for contractual reasons that we usually have very little control over, and becomes a paper-based flat delivery, so to speak. And that happened a couple of times actually, back and forth. And it has, if you've been involved in it, you know that it has to do with liability and the way that we kind of still, as an industry, haven't really figured out how to write proper contracts from either side, so that everyone can feel that they're conveying what they want to, no more nor less, when they hand off a 3D model, or for that matter, just preparing it to sort of minimize their own staying up at night worrying about it, and worse. So that's I think an ongoing, and I'm happy to talk about that later if someone vehemently disagrees with me. But I think it's on all of us to get better at this, and I don't think we're at all there yet. But in this case, it went back and forth again, and eventually became a paper-based delivery, which is why all of this needs to happen, so that this can basically be delivered in a traditional design bid build sense where, somewhat simplified, we hand up a stack of paper, and someone has to interpret that stack of paper without any contact with us, right? That's the sort of extreme form of it. So this is the attempt to give this to someone on the contractor side who can basically pick it up and just build it from the instructions in the drawing set. So for that reason, everything is dumbed down, if you will, or rationalized, if you prefer that, I stand by both of those definitions. They're into primitive geometric shapes that represent architectural entities. So here you have an ellipse, which in this case represents the top edge of a specific drum of this global geometry. So an ellipse has a long and a short radius and a center point and a plane that it lives in, which is all you need to really define that ellipse. And then once you have those points in the plane and the two radii, the minor and the major radius, then you know what that ellipse is. And the other information, of course, you need in order to figure out what this blue ribbon here looks like is that you need to know where on the ellipse does it start, where on the ellipse does it stop, and then there's another ellipse that in this case, in a corresponding way defines its lower edge, and with a start and stopping point. And then those two sort of subcurves from these two ellipses are then, they become the edge curves for a ruled surface, and that becomes the definition of this particular piece of rationalization level 1 geometry. And then that goes on into slightly more intricate ways sometimes. For instance, here, because of the architectural kind of situation, this has an undercut, which is then achieved, which is it's neither parallel to one of the ellipses, nor is it in the direction of the plank lines of the surface. So this becomes one of those strange NURBS curves that changes radius continuously. But you can describe it by undercutting, in this case, the ruled surface with a plane that has a certain equation to itself, so that you don't actually really have to care what the dashed red line is. You just know that it's whatever is the product of the intersection of the plane and the ruled surface. And so that is what comes out of that, right? And then from there, if you extrapolate what I just showed into all of those shapes that were in the colored overview diagram before, then that goes into the level 2 rationalization from this diagram that you might remember. More specifically, these are mega panels of usually between 8 and 10 metal panels that are in themselves 8 feet wide by 3 feet tall. So when they are pre-assembled into mega panel kind of structures, they're about between 24 and 30 feet tall by 8 feet wide. So that sort of, and that is a flat plane, right? Each of these is a planar object, which when you are analyzing a curved shape like this, if for architectural reasons of architectural design intent, your panel joints can't necessarily always trace the plank lines of the ruled surfaces, then you get either curvature in your panels, which you kind of don't want, because then you're going to have to start curving your mullions and your metal sheets and whatnot. So you either do that, or you do a study in which one of the 4 corners, all 3 corners can always lie on a plane, right? But the 4th corner, whichever it may be, is going to poke out or in. I'm sure you've all done this type of exercise, and that's a pretty easy study to do. What's not so easy is to convince a client whether something which is poking out by 7/16 of an inch and which is 50 feet up in the air is actually visible or not. Luckily, I'm jumping the gun here a little bit, the client did agree that that wasn't going to be an issue once it was put into context how little this fourth corner pokes out. And more interestingly, the eventual fabricator contractor who was end close, but we didn't know that at the time, but they just decided that they would cold bend these panels into place. So you see the note at the bottom there, you see with a 1/2 inch offset over 20 feet, the warping when you do that is so little that you can just force it into place on site. So that's what they did. But we didn't know that at the time, but thankfully the client believed us when we said that this is not appreciable at the scale that it happens, which obviously saves a massive amount of money compared to fabricating these actually curved. Similarly, because there's a bunch of stuff, as you see on the right-hand side here, that needs to go between structure and skin, there's an offset that needs to be respected for where the slab edges occur. And we don't always set out slab edges. That's usually the primary structural engineer. I mean, we don't do that when we're not the primary structural engineer. In this case, we did because we had the control of the skin geometry, so it became logical for us to own that too. And now this slide is a little bit grainy, I think, but you can probably see how the sort of arc nomenclature is defined in those arc composites along the kind of grid line system. And this actually, if you look to the right here, the sort of the blow up of to the left, you see that the black line is the faceted actual skin, those metal panels, or in certain cases, glazing panels that you saw before. And then there's an offset. I believe it was something like 1 foot or 16 inches or whatnot. I don't quite remember, but it was defined by kind of how the curtain wall detailing worked and how it needed to be hooked into the slab. So that was offset back, and then actually, and this may or may not have been overkill, but it was sure fun. The rationalized so-called slab edge, according to my level 2 definition, is a composite arc shape where the individual arc radii and their tangencies are actually produced using a genetic algorithm. More specifically, it was done using Galapagos in Grasshopper, because there are infinite amount of arcs that can be tangent to each other and not necessarily the quote unquote best or fittest version of it. So we left that to the automation engine and probably could have made our lives easier, but that seemed like a good idea at the time, and it worked out. And that became the slab edge setting out kind of mechanism. So here you see again the cladding, the rationalized contour, and then the slab edge. So the rationalization actually happens at the level of the skin and then gets offset back. Okay, so going into documentation then, maybe this is about halfway. So maybe I should stop here and ask, because this is a sort of water divide. So Lauren, are there other questions that I should be aware of?
Yes, there is a question here. Do you perform structural analysis locally in Grasshopper environment or export to structural analysis software?
That's a very interesting question. We have done historically some quick studies in things like Caramba and Millipede. However, we are very blessed, I must say, in our team to have a very high level of computational savvy on the engineering side. So I'm an architect by background, and a lot of the people who work in the facade engineering group are also architects. But we do have people that have structural engineering background, and not always are people from structural engineering education very computationally educated, right? Because it's not, structural engineering is many times is not a design driven or sort of a project driven education, right? It's many schools do it very theoretically, but we have been lucky to been able to put together a team over the years where there's a very high level of competency in that regard. And that means that a lot of this can be done directly by the engineers in the softwares that they then prefer to work in for the more detailed analysis, such as SAP or GSA or Strand, usually. But that's a good question. I have done personally some early stage analysis in my life, and I'm not sure I should be entrusted with it.
One more, and then you can get going. Who was ultimately responsible for determining budget constraints, and how has that affected the panel spacing you showed?
Great question. So if you saw that little sort of contact sheet of many different facade area models, a bunch of slides back, so one of those became the one that kind of became the source of truth in a way with regards to square footage, which in itself is driven by cost. So at some point in the schematic stage, basically, that was decided based on the best kind of estimate of what that led to in terms of a per square foot enclosure cost. And once that was decided, then that couldn't change. And similarly for the panel joints, actually, I'll flip to the next slide because it's anyway showing an elevation of panelization. In terms of the panel joints, that was an interesting in itself exercise because you see all those. So there's two very sort of intricate architectural things at play here, aside from the geometry and the assembly fabrication logic that we were sort of trying to steer, and that's you see all those horizontal punched holes in the panel are light coves. You'll see that in the real life photos of the building later, especially at night. And it's beautiful, but like that patterning became a very strong design driver, understandably, as well as the somewhat impossible task of aligning joints from all view angles. As you can imagine, that is not possible when you have round or elliptical drums that sort of weave in and out of each other almost like this, and sort of with different offsets in on the plane. So there were a lot of architectural owner interactions for what is the sort of best kind of joint spacing and set out so that the lines kind of look pleasing to the eye from the most angles possible. And we just stayed, we stayed part of that machinery basically. So whenever a new iteration came from the architect in conversation with the owner, which we were many times also part of, we would reset that out basically with the ultimate goal also of creating a consistent width of panel, because that has its own benefits, of course, on the fabrication assembly side. Does that answer the question? I tend to use many words when I answer questions.
I believe you're good.
Okay, should I keep going?
I have one more question.
Sure.
I wasn't able to type it in. You discussed how the stage 1 or level 1 rationalization, you were able to define a complex NURBS curve as an intersection between a simple plane and a simple ellipse. I wonder why is it necessary for that sort of simplification if we now have the ability to extract very complicated data? We don't need to manually calculate anything anymore. So what are the advantages of that kind of rationalization?
That is yet another great question. Let me see if I can flip back to that particular slide.
And if it's something you're going to get into as you talk about how it's documented, we can continue, of course.
I am, yeah, but I think this I'm not sure if I have this particular one on its drawing sheet. This is a little bit of an oddball because most of these were not undercut this way. They were actually with a true elliptical or subset of an ellipse as their edge curve. So at the time that this diagram is drawn, to the best of our knowledge, someone needs to reconstruct this whole model from, the information that you see on the screen right now and similar. So that's the reason, really, unless I'm misunderstanding your question, that we don't want to get into having to describe this with, you can describe this, right? Mathematical, but it's beyond my capabilities and beyond most people's to do that in a clear and understandable fashion, short of actually giving a piece of geometry to someone. So the idea was, if I tell you how to build your curve and then how to build your ruled surface between ellipses and then the plane that needs to cut that, then you can create this red dashed curve without that you necessarily need to care about what it is. You just know that it's the result of other things. Does that make sense?
It does, thank you.
Okay, great. All right, I need to move the, I'm not fortunate enough to have 3 screens. I need to move this out of the way. Okay, I will click forward again to Zuby. Shall I keep going, or was there anything else?
Yeah, keep going.
Okay. All right. So that was a good, I think, halfway point here when we get into documentation. So as I said, this needed to be documented in the traditional way. So this is all Revit 2014, I think, 15 perhaps. It's you know, in most projects that I've worked on, once the project starts, you don't upgrade Revit version just for you know, for sort of policy reasons. I think it's 14 or 15. This was all brought in with kind of custom methods from the Rhino. All the rationalization of both levels and all of that was done in Rhino Grasshopper, and then brought in with kind of in-house tools that we have these days. We would probably use mainly Rhino Inside for things like panel transfer, but we also have our own internal database transfer tools that we typically prefer, because we can customize very high-level customization in the kind of attributes and metadata that comes with. But anyway, here you see this is a very typical classic kind of architectural elevation with levels and everything, and behind that kind of lies all of these diagrams. So this comes to the speaks a little bit to the gentleman who asked the question just before. How that got sort of inserted into kind of a drawing delivery logic, and this is the answer to that. So you have these, pardon me, different diagrams that, excuse me, different diagrams that describe each of these drums that have been previously defined in terms of like what they're called and where they are in the global system. And then to the left, it's a little bit grainy. I hope you can read it. Or at least see what type of information it is. So on the left there, you have tables basically, which correlate the names of these different points, planes, curves, whatever it may be, and then gives a coordinate in decimal feet, I believe, to the 6th decimal, which can always be, I suppose, discussed whether that's necessary or not, but that's what we did, just to be safe. And then that kind of goes on. So yeah, these are the design surfaces identified, as I say, by edge curves and corner vertices. Those are the work points that help you do that. And this is kind of the exploded axo that shows how the building comes together, that kind of, in this case, defines zones or quadrants, which will then further help to sort of identify where the elements belong. You see here, this is a zoom in on one of the atriums. So the atriums in themselves actually are interesting, because that's what's ultimately going to get tested for performance purposes. Because if you remember when I showed before how the rain screen is assembled, or is rather the structural load path follows the logic kind of traditional curtain wall, and then there is actually some actual curtain wall also in the building, which are the 2 atria more specifically that are face sealed glass, long span systems instead, and they need to be something that's called mocked up for performance testing. If you've ever been to one of these, it's pretty cool. I hope you get to do it if you haven't. It's a couple of different companies across the world and in the US that do this full time. These are testing labs basically, and they have, various kind of decommissioned plane engines that are blowing water at a certain predetermined speed. So you simulate very, very sort of strong wind-driven rain from the side onto a full-scale portion of your building that has ideally been built by the same people that are actually going to build the building eventually. That is not always possible, but in the best of cases, you manage to get the same people so that they actually learn from whatever might not have worked the first time around. In this case, it passed. So here's, you see some of the curtain wall detailing on the inside as the wind is kind of hitting, the wind-driven rain is hitting the glass on the outside. So there, to the left there, you see the spring. That's the bottom detail for one of those hanger rods, which is a cold spring inside of a housing that ensures that this rod will, because it's not a cable, right? It's actually a stiff member, but it's not supposed to ever go into compression, so that if that were to ever happen, then it would just bounce on the spring basically, and for the rest of the time stay in tension. On top right there, you see one of the pin connections that make up one of those lateral braces that I talked about before, and then bottom right, that's the image you've seen before already. That's a curtain wall anchor. So that's the top gravity connection. And here you see the wind beating down, the rain, sorry, the wind-driven rain beating down on it, and nothing coming on the inside, which means that it passes the mock-up, which is great news for everyone, and life can move on. So finally going on site then, and at this point, of course, contractors had been novated, and Close had very successfully rebuilt the full sort of high fidelity geometry from our drawing set, and then actually eventually, and I'm not sure I'm supposed to say this, but eventually it was contractually resolved and we could just give them the model. So it was it was not all for naught, but it could have been done differently. But many times that's how things go down, right? You don't know at the right point in the process kind of what's going to be possible or not. So you have to prepare for sometimes you have to prepare for like the most primitive in a way form of delivery, even if that doesn't come to pass in the end. Summer of that same year, the foundation work is close to done. You can see the rebar cages for the primary columns coming up the ground. Going to the mid autumn, early winter of that same year, you got the two cores, circulation cores are up, and first floor slab. And then by the end of the year, it's really starting to kind of take off in speed here, building floor by floor with the primary structure, and starting also to put, you see, these are those cold formed stud grids that are eventually going to hold the weather barrier behind the rain screen, the ones that I showed in the diagram before again. So this is now a year into construction. Sorry, by the time of the summer, about a year and a half into construction, you see a good deal of a good chunk of facade has been installed already, and that black surface there is that's the rain screen, the facing of the installation of the rain screen behind the metal panel. And August 7th, 2018 is a year out of completion, and then I don't have any earth cam pictures anymore, but I do have some real photos from when I was lucky enough to not only go there but get a kind of glorious day in the strange San Francisco November weather, with just enough people there to see that the space functions really successfully, but not so much that it becomes kind of hard to take good pictures or move around. So here you see, and I mean it's actually quite remarkable. Again, I must kind of stress how well thought out it is for this particular project to have thought of its larger urban context and the impact it has on the place that it sits in, complete with this thing called the Gatehouse, which is by shop architects, which is the kind of gate, as the name implies, between the city. Right behind her is the light rail, the Muni San Francisco public transit system station that is for this stop specifically. So you get off and you hit this kind of structure immediately. And this, by the way, is sort of this is an academic paper in and of itself. It was extremely difficult to model and document, but that will be for another time. It suffices to say that it's again a beautiful structure, in my opinion, and a very successful very successful public space, just the same as the rest of the project. So now I think I'm just gonna flip through some images of that that I threw in here. Whoops, that's actually a repeat of that. That was not intentional. I apologize for that. You see, here's a curved glass curtain. Well, this is by the way, where they do the television. They make this into the TV studio when there's game day and other events too, I think. So this is sort of very very functional as well as a beautiful object, I think. Some details of the curved glass, long span curtain wall, and here's another part of the project that was also built at the same time, which is part of those 500,000 square feet of public mixed use development with a public space in the middle. And I think we will now get to the conclusion. There we go. So what we tried to convey with this sort of geometric recipe making, if you will, is that we don't pretend to be scientists, of course, by any stretch of the imagination, but we do take some inspiration by the scientific approach, where you try to compartmentalize and discretize the things that you do and build upon your previous experiences in a formal way for the future. Once, of course, it's hard to create sort of clean, quote unquote, lab conditions, because every project is messy and unique and all. But we still think that we have a reasonably good handle on how to kind of extract first principles from projects and to, if not reuse them, at least consider them in a useful way for future work. So another way of saying that is we aim to build institutional knowledge which benefits both our own practice as well as the wider community that we work within. And this goes back to what I kind of mentioned before about 3D product delivery. Of course, we would love if we did away with drawings altogether, but we're not near there for so many different reasons. I mean, just if any one of you has ever been to any department of buildings of choice, you'll see how far away we are from proper 3D procurement and delivery, right? So therefore, we need to have sensible, functional, parallel methodologies in our opinion. And finally, we believe that each project is best approached as a complex organizational task with an uncertain outcome. Therefore, to have these points on the table at all times helps navigate each and any project trajectory. And that concludes my talk on the dot 49 minutes. Thank you.
Fantastic. Thank you very much, Gustav.
Thank you.
As we process some of the questions that are coming in, a poll is going to come up just so we can get some understanding of the audience attended here today. And then we'll transition into the panel discussion.
Okay. So I'm reading the Q&A here. So should I just hit it that way?
Oh, do you mean the Q&A is just for everyone, to fill in, and then the questions, if you want it, do you see the questions or?
I see the question and answer and I see the poll.
Yes. Yeah, you can get through the poll and get to the questions.
Actually, I'm not allowed to poll.
Okay, then that's fine. So it looks like we have 4 questions here.
Yeah. Okay, so I'm just gonna hit from the top then. Meyer Mystery asks if there is any rationalization for perforation in facade panels, or is it randomized? It is both, actually. So there is there was a request for a percentage of what the total sort of percentage of perforation needed to be X. something. And also on a more mundane note, you know, in some cases you didn't want, like a slot might be randomized and the percentage might be correct, but then a slot might be in front of a structural member and you can see the structural member through it. Then you'd have to move it. So it was the classic, the way I remember, it was the classic kind of 90% computer, 10% manual moving things when they were where they shouldn't be, which was faster than, obviously we could have scripted it, you know, don't end up on a structural line. But that wasn't really worth the time in the end. Okay, anonymous attendee, in terms of managing the script, how was that handled? Did anyone have access to modify the script, or was there a designated person that had exclusive access? Any lessons learned? Oh, anonymous, you don't know. Yeah, you probably do know actually how how unsolved that problem is, I think, for everyone. So the short answer to that is we did a lot in Grasshopper. We had the usual woes of Grasshopper, meaning the kind of thing that grows into a spaghetti monster that only one person can manage in the end. We have for years been actively combating that by doing a combination of user objects and shared clusters, more specifically, because we have decided kind of years ago already in our team that we don't want to make coders out of everyone. There are specific people that are very good at coding. There are specific people that don't know almost a line of coding, but they're amazingly good at Grasshopper modeling, and we don't necessarily feel that either of those need to be shoehorned into the other role. So we tried to modularize the visual programming scripts, definitions rather, as best as we can, and with varying success, I would say. I mean, you know, we're still guilty of the odd spaghetti monster, but we're much better at that now than we were 5 years ago. So now we have actually a baseline collaborative environment on the Grasshopper canvas, if that makes sense. Okay, Mayor Mystery asks, for curved slabs, what would be a framework to decide whether to provide curved glass or segment it in direct linear panels on the curve? Okay, so simply put, there is never, a strictly speaking, a need to curve glass unless you want to. Like you can, with the offsets that you anyway need for a curtain wall, you can almost certainly always facet a reasonably sized curtain wall panel on a slab edge that's curved behind it, just in terms of geometric setting out. Whether you want to do that or not is a whole other question. Of course, you saw here, you can go back to show the gatehouse that I talked about. One more here. So this here is curved because of design intent, and it could just as well not have been curved, but it wouldn't have been as beautiful as it is. And at least that's my opinion about it. And in the case, and this of course doesn't have a slab behind it except for the ground floor slab. This is just a long span kind of tall glazed curtain wall. If you look at say this here, so this atrium here made out of glass, or the side here, again, none of this would have, you know, quote unquote, had to be curved. So that's almost always just a design intent question, not a geometric necessity. I don't know if that answers your question properly or not, but I think that, yeah, we'll have to move on to the next one. So I hope that answers your question. Alejandro Nunez, was the Walter P. Moore team involved full time from start to finish, or was there a handoff at a certain point and fabricators / Kendall Heaton, that's the architect of record for those who didn't remember that, handled the final assembly and detailing? So the typical way that an enclosure engineering consultant like us is involved in a project like this is that we get brought on quite often in sort of SD phase, unless it's a competition or a design build bid or something like that. But in a typical case, we will get brought in when there are some project, specifics that are pinned down already, some sort of early SD level, quite typically, and then work all the way to the end, to when the project is inaugurated. That doesn't mean that there aren't handoffs of sorts, but not handoffs in which we then walk away. So once you have, in this case, handed off the bid set, the construction documentation set to the contractor, sometimes you get told, okay, thanks, we'll take it from here. In most cases, especially with experienced clients, which is naturally preferable for us, they sign you up for construction administration scope as well, meaning that we will then be a reviewing party of all the work that gets done by the architect of record, or rather by the contractors through the architect of record reviewing and together with us. So the final assembly and detailing, that goes out in terms of typical details in that case, and then ultimately the contractor will make a shop drawing of every single situation, everything, single condition in the whole project, and we will review that and say, either this is fine or this is not fine because A, B, and C.
All right. We'll transition now to the
There's actually one more question, Zubi, sorry, that I'm actually quite interested in answering.
Okay.
Can I?
Yeah, sure.
Yeah. So Anonymous asks, are you part of the hiring process, and how do you make sure they're not just saying the right words in the right context, but you can actually execute? Is there an assessment you can make them take? We do not have the CAD test or the modeling test or the BIM test or whatever. I have never, and maybe I will be proven wrong on this, but I have never met someone who can talk convincingly about computational design in terms of actually doing the work and eventually turns out to not be able to. I think it's such a messy and specific thing that the only way to actually know how to talk intelligently about it is to actually know how to do it, or at least having known how to do it at some point in life. But I might be proven wrong, but I haven't seen that before. So this is basically a at least in my experience, it's a non-problem.